For most of human history, darkness was not an inconvenience, it was a hard boundary. When the sun set, productivity ended. When you went underground, you brought fire, smoke, and risk with you. Light was expensive, fragile, and dangerous. Today, we flip a switch without thinking. But 2,000 years ago, long before filaments and grids, engineers were solving a different problem. How to bring sunlight deep into stone structures without flame, without smoke, and without fuel. They did it with geometry. This is the story of the ancient light tube, a deceptively simple architectural device that redirected daylight into underground rooms, corridors, and storage chambers. It required no electricity, no glass bulbs, and no combustion. Only an understanding of angles, reflection, and the movement of the sun across the sky. And in an era of rising energy costs and windowless urban basements, it might be more relevant than ever. Ancient civilizations built downward for many reasons. Subterranean rooms offered thermal stability, protection from heat and cold, security from attack, and long-term food storage. Across the Mediterranean, underground granaries preserved grain through scorching summers. In arid climates, descending into the earth meant entering a naturally cooled environment. But underground space comes at a price: darkness. Torches produced soot that stained walls and lungs alike. Oil lamps required constant refilling and introduced fire risk into enclosed stone chambers. In food storage areas, smoke contaminated supplies. In religious spaces, flickering flame distorted sacred geometry and iconography. Engineers began asking a simple question: could the sun itself be guided underground? Within the architecture of the Roman Empire, we find early examples of controlled daylighting. Roman houses commonly featured an atrium with a central opening called the compluvium, which allowed light and rain to enter from above. Beneath it sat the impluvium, a shallow basin that collected water. This pairing was both hydraulic and luminous, managing rain and sunlight simultaneously. But beyond open courtyards, more refined systems appeared in bath complexes, hypogea, and storage vaults. Vertical shafts were cut through stone ceilings, often narrow and angled, to capture sunlight from specific orientations. These shafts were sometimes lined with pale plaster or polished surfaces to amplify reflection. In certain subterranean corridors, bronze or polished metal plates were installed to redirect light deeper into interior spaces. While mirrors as we know them today were rare and expensive, polished metal could function as a reflective surface sufficient to redirect beams of sunlight. This was not accidental architecture, it was solar engineering. By aligning shafts toward the southern sky in the northern hemisphere, Roman builders ensured maximum light penetration throughout the day. The sun's seasonal arc was understood well enough to predict illumination patterns. In some cases, shafts were flared at the top and narrowed below to concentrate light downward, increasing brightness at the chamber floor. The principle was simple: capture, reflect, and channel. The Roman world was not alone in this innovation. In ancient Egypt, light shafts were incorporated into tomb architecture. Narrow vertical openings admitted thin blades of sunlight into burial chambers, often aligned with significant celestial events. These shafts served symbolic and practical purposes, illuminating walls while preserving structural integrity. In the underground cities of Cappadocia, carved into volcanic tuff, vertical ventilation and light shafts penetrated multiple levels of subterranean habitation. While primarily designed for airflow, these shafts also admitted daylight into communal spaces. Across the ancient world, the idea persisted: if the sun could not enter directly, it could be guided. At its core, the natural light tube operates on three physical principles: reflection, angle of incidence, and diffusion. When sunlight strikes a reflective surface, it leaves at an equal and opposite angle. By placing angled reflective plates inside a vertical or diagonal shaft, builders could bend light around corners and down corridors. Each reflection reduces intensity slightly, but with sufficiently polished surfaces and short distances, usable light remains. White or pale plaster increases diffuse reflection. Instead of a sharp beam, light scatters across interior surfaces, producing soft ambient illumination rather than harsh glare. Some shafts were straight and vertical, relying on direct overhead sun. Others were angled to capture low morning or afternoon light. In certain reconstructions, a sequence of angled mirrors functioned almost like a primitive periscope, bending sunlight through multiple turns before releasing it into a room below. No fuel was burned, no heat was generated beyond natural sunlight, no ongoing cost existed once construction was complete. The system ran on astronomy and geometry alone. Underground rooms maintain relatively constant temperatures because soil acts as thermal mass. In hot climates, subterranean chambers remain significantly cooler than surface structures. In cold climates, they stay warmer than the winter air. The challenge has always been illumination. By integrating light shafts, ancient builders combined thermal stability with daylight access. This created spaces suitable for food storage, religious gatherings, and even habitation without reliance on combustion-based lighting. In effect, these systems were early examples of passive design, long before the term existed. If this technology is so elegant, why is it not common today? The answer lies in cheap energy. The Industrial Revolution decoupled architecture from solar constraints. With the advent of gas lamps and later electric lighting, buildings no longer needed to align with the sun. Basements could be buried deep and lit artificially. Interior rooms could be placed far from exterior walls. Energy became abundant and geometry became optional. Architectural literacy and solar movement declined as grids expanded. Builders prioritized square footage over daylight pathways. Mechanical systems replaced passive solutions. The skill of carving precise solar shafts through masonry faded into obscurity. It was easier to wire a bulb than calculate an angle. In the late 20th century, daylighting engineers quietly reinvented the ancient concept. Tubular daylighting devices, often called solar tubes, consist of a roof-mounted dome that captures sunlight, a highly reflective internal tube, and a ceiling diffuser that distributes light below. The interior of these tubes is coated with materials that reflect over 98% of incident light. Even with multiple reflections along bends, the loss remains minimal. A properly installed tube can illuminate a basement hallway or bathroom without any electrical input during daylight hours. The principle is identical to the Roman shaft. Capture, reflect, channel, diffuse. What changed is material science. Instead of polished bronze, we use aluminum alloys and micro-layer reflective films. Instead of rough plaster, we use optical-grade diffusers, yet the concept is 2,000 years old. The core requirements are simple but precise. First, orientation matters. In the southern hemisphere, north-facing surfaces receive the most consistent sunlight. In the northern hemisphere, south-facing exposures are optimal. The shaft should intercept the strongest portion of the daily solar arc. Second, reflectivity determines efficiency. Smooth, highly reflective surfaces outperform matte finishes. Even white paint can significantly increase brightness compared to raw masonry. Third, distance reduces intensity. Shorter shafts provide stronger illumination. Each bend introduces loss, so minimizing angles improves performance. Fourth, diffusion at the exit point prevents glare. A translucent panel spreads light evenly across the room, mimicking the effect of a skylight rather than a spotlight. When integrated thoughtfully, such a system can transform a windowless basement into a usable daytime space without adding a single watt to the electrical load. Ancient builders treated light not as decoration, but as infrastructure. It was engineered alongside water channels, ventilation shafts, and load-bearing arches. Sunlight was not something that happened to a building. It was something the building was designed to conduct. This mindset shifts architecture from consumption to cooperation. Instead of overpowering darkness with energy expenditure, the structure collaborates with celestial mechanics. The sun rises, the shaft receives, the room brightens. There is no monthly bill for sunrise. As cities grow denser and energy costs fluctuate, passive systems regain relevance. Climate-controlled underground spaces are increasingly attractive for resilience and efficiency. Integrating daylight into such designs reduces psychological strain and energy demand simultaneously. The ancient light tube demonstrates that low technology does not mean low sophistication. It represents a convergence of astronomy, physics, and architecture achieved without silicon chips or copper wiring. It also reveals something deeper. Civilizations that studied the sky carefully built structures that responded to it. When that study diminished, so did the structures. Relearning solar geometry is not regression, it is continuity. 2,000 years ago, an engineer stood in a stone chamber and imagined sunlight descending into it without flame. That engineer cut a shaft, polished its interior, and waited for dawn. When the sun rose and the chamber filled with light, something fundamental shifted. Darkness was no longer absolute. That moment did not require a power plant. It required observation. Today we live surrounded by electrical abundance, yet many of our spaces remain artificially lit even at midday. The solution to some of that inefficiency was carved into stone long before wires crossed continents. The natural light tube is not a relic. It is a reminder. Geometry can replace consumption. Design can replace dependency. And the sun, which has always risen, can still be invited indoors without a switch. If you enjoyed this video, don't forget to like and subscribe so we can keep improving the channel. See you next time.